So basically the greedy is a techniques. Okay. Mm, what happens, suppose you are in a particular state means this is the position means not physical positions. You would like to compute some optimal solution. Okay, you have been given an objective function that you have to maximize or minimize some things. Now you are trying to find out the solution. Now there may be so many paths, means so many ways to solve this problem. You may go like this, you may go like this. Okay, now if you it is your current positions, this one is the current positions. Now you may have the next position, these are the next position. Or suppose I am saying you are in, I am in the Durgapur, I would like to visit Kolkata. Now there are so many paths that leads to Kolkata, means this is the path, this is another path, this is another path, this is another path, this is another path. Okay, and there are some next stations, means these are the hops, I can say. So through which path should I go so that I will reach the Kolkata in uh, minimum amount of time, or it will take minimum cost, like this type of problems. Now you see, when I am in these positions, when I am here in these positions, I do not know all the values. All the values means all the path lengths are not known. So it may be the path length is suppose 12, this may be 24, this may be 100, this may be 30, just next stop, and this may be 80. Okay, so this is 30. So here you may think that, okay, if I visit the nearest station, means next stop, see how many next stops, 1 2 3 4 5, next stops are there. So if I visit mm, the this one, then I am seeing that I need only rupees 12, or say 12 kilometer, or distance to reach the next station, whereas the others needs much more time. So I will visit this. So but you please remember, once you visit this, there is no guarantee that this path length will be the finally, or whenever you will reach to the Kolkata here, then it will be it will give the minimum path length. No guarantee. Okay, so there may be that means whatever what you are doing, actually you cannot see the all the path lengths that reaches to Kolkata. But at present, you know that I have these many options. At present I am here locally, I have these many options. Out of these, this is the best one. So I expect if I follow this path, then I may be benefited than the other paths. So that's why I am visiting. So I am greedy. I am greedy to choose this path. Clear? And the decision is based on the local optima. So is basic. Please remember one thing, that this is based on local optima. But there is no guarantee that whether these will give the global optima or not. Global optimal solution may or may not be reached. You may have so many greedy idea. Okay, you may follow, but there is no guarantee that it will give you the global optimal solution. Finally it will be optimized. And that's why greedy algorithm are very easy to design. Okay, for the same problem, suppose you are designing a greedy algorithm, I am also designing a different greedy algorithm. Your greedy algorithm may give optimal, my greedy algorithm may not give the optimal solution. But what is the difficulty here? The difficulty is that if the greedy algorithm gives optimal, the proof of correctness must be present. Means you are saying that I am following this path, so I will get a solution, and this is the optimal. Why you are saying that optimal? You must show the proof. Okay. So here now I am just saying you a simple problem first. You see, suppose you know suppose this is a graph. Okay, this is a graph. like this. Now in the graph G, I have a set of vertices and a set of edges. Now what do you mean by independent set? Independent set is a set of vertices, say V1, which is a subset of V, so that Vi, Vj, this pair does not belong to the edge set E. Means they are not connected, where I is not equal to j. For example, here suppose I am writing like this: V1, V2, V3, V4, V5. Now here, if I choose this vertex V2, then you see I can choose V5, because V2 and V5 are not connected, so they forms an independent set. They forms an independent set. Similarly, you may choose say V1, V3 or V1, V4. In this case, I am saying whatever be the case, the maximum size is 2, independent set. But there, I am not drawing. You may draw yourself, that you are drawing, say, a graph with 10 vertices or 12 vertices, and you randomly assign some edges between the two vertices like this, and you draw the graph, and you will get that say there exists so many independent sets, and there may be a independent set of size say 5. Means while 5 vertices are there, they are not connected to each other. So that is the maximum independent set. Now you see the easy problem is that easy problem is you just select only one vertex, that is also independent set. Okay. So anyway, the difficult problem is that if anybody asks you that you for can you design any algorithm which will give the independent set of maximum size for any graph, then it is very difficult problem, NP complete problem, that we will learn later in this course. So hard problem. So that is very difficult. But the problem may be easy if I change the graph to a tree. For example, I have been given a tree like this. The tree is like this. In this way, the tree is there. Okay. Randomly, you can assign as many as edges as you want. So these are the, this is the nodes, and these are the edges. So basically this is the tree. Now if I ask you the problem that solve the same problem, that find out the maximum independent set, find out maximum independent set. So for graph it is very difficult problem. Okay. Now for uh, tree, how can I solve this problem? So here you see I can choose that, okay, independent set means the two vertices should not be connected. So what I will do, I am drawing here. Suppose I am partitioning the tree into two sets, where these are the leaf nodes, and there are so many other. Here you check. Okay, I am not drawing complete like this. So like this. So what I will do, I will delete all the leaf nodes of T, and what I will get, the tree T will reduce to another tree T prime. So now here you see these nodes are not connected to each other. So all these nodes, leaf nodes, forms the all these leaf nodes forms the independent set. Fine. So I am collecting these one, these one, these one. They are not connected to each other. Clear? Check it. So I am covering this. On in the next level, what I will do is I am deleting. Okay. Then you check it's, or you may not delete. If you I was just telling to delete for your so that you can understand that, or you can directly say that you don't need to delete. Okay, you just consider all the leaf nodes. Better you should write consider all the leaf nodes of tree. Okay, now what happens after this? In the next level you check, you select this one, just two levels above. Okay, two levels above means these nodes.
Sir, as in two levels above the leaf node.
Hello.
Sir, as in two levels above the leaf node, sir.
Because you see, if you select this one, then this cannot be selected, means just its parent. Its parent can be selected, tell me. Then they, it should be independent set, means the two vertices should not be connected. Are you getting? So if I select this parent node, then parent node and the child node, they are connected. That's why I'm saying that don't select its parent, but you select the grandparent. And in this way, again its grandparent, it will be selected like that. But this is a greedy algorithm, and you have to prove that uh, this gives the optimal solution. This gives the optimal solution. Just I can exchange. See what happens. Suppose I am getting in this way. If I get a set of nodes, and I am claiming that that will be the maximum independent set, capital I. This is the solution. Is there a solution by us? And suppose there exists an optimal solution, capital O. This is optimal solution. And someone says that optimal solution has more number of nodes. I am claiming no. Our solution will have also the same number of nodes. How can I prove? Okay. So here you see in the leaf nodes, all the leaf nodes are in my set. So if any of the leaf node is not present in the optimal set, suppose I am choosing this. Suppose this leaf node is not present. You see, this leaf node is not present in the optimal set. It is not present here. So what can I do? So if it is not present, I am sure then this node must be present. Probably. Or say this one means what I am saying, that then I can see if this node is absent, then I can replace, means one of the solution, means suppose it contains x, while this x is absent here in this case, and this is suppose y. So I will replace these x, these y by x. Means I will tell that okay, you delete x and insert y here, so that the number of node remains same. That means actually I will change the optimal solution to my solution by just replacing the nodes. So this example I have told you informally because this is easy problem. You can try yourselves, and you will get the proof. So now today we will means so the new problem, more interesting problem. The interesting problem is that you see, say interval scheduling problem. Interval scheduling problem. What do you mean by interval scheduling problem? Suppose I have a set of jobs. Fine, I have a set of jobs. Now all the jobs has starting time and finishing time fixed. Suppose you assume that this job will start at this time and finish at this time. This job will start at this time and finish at this time. For example, this job will start at um, 0 time and finish 6. This job starts at time 1 and finishes at 4. In this way there are n jobs. Fine. So, and you may assume that uh, here you see schedule as many non-overlapping tasks as possible in a given time frame. Means our objective is what? I have only a given CPU, only one machine is there, and I have been given some jobs. Now there should not miss. You assume that no two jobs can be executed at the same time. Means no two jobs can be executed at the same time in a CPU. I'm assuming. Okay. One machine. In a single machine, you cannot execute parallelly two jobs. And another thing is that these are the assumption. So there are no preemption. Preemption means suppose you have started job A, and after 2 units of time, job A will release the CPU and C will be given, and then again A will start after C has finished. No, we will not allow this. Means once a job starts, it will keep the CPU until it finishes completely. Okay, it will not release the CPU until it finishes completely. So that means there are no preemption. Preemption, what do you mean by preemption? You will learn in the operating systems. So preemption of a job means once a job has started, now say there may be the case that some higher priority job has arrived, and the lower priority job has released the CPU to the higher priority, and lower priority job will start later. No, this will not happen in this case. That are called preemption. So no preemption, and no two jobs can be executed at the same time. So uh, the problem is clear. The problem is that you have to find, means you have to assign which the jobs, so that the total number of jobs that will be completed is maximized. Did you get the problem? I am not telling the solution. Tell me yes or no. Objective is to find out the set of jobs, maximum number of jobs that can be executed on a single machine. Only one machine is there. There are n number of jobs, and I have to execute maximum number of jobs. I cannot execute all the jobs, because if there is an overlap, then I cannot execute all of them. Only one of them can be executed. But how should I assign the jobs? Means how should I execute the jobs so that the number of jobs that are executed is maximized? This is the problem, and this problem is called interval scheduling, where an interval is used to denote a jobs. Is an interval, see here, job J starts at Sj and finishes at Fj. There are two times Sj and Fj. Okay, so Sj comma Fj denotes a job J is starting time, finishing time, and two jobs J1 and J2 are said to be compatible if they do not overlap. Compatible means they do not overlap, they can be executed separately, no problem. But not compatible means there is an overlap, only one of them can be executed. So find maximum subset of mutually compatible jobs. Our objective is to find maximum subset. So this is the time. Now This is the time frame, and this is the starting time. Its starting time is 0, finishing time is 6. Okay, 0 to 6. Here it is 1 to 4, like this. So all the uh, starting as time and finishing time are given. So how can we do this? See, there may be so many greedy techniques. What are the greedy techniques? See, here see, I will obviously whatever be the greedy technique, I will take the each job provided it is compatible with the ones already taken. Means once I have started a job, then I know it will finish. But in the next time, whatever I will select, that must be compatible with the previous one. That I know. That is otherwise it's not possible. Now there are some greedy idea. Greedy idea means choice. Whatever you are choosing, that is called greedy, means locally optimal. So here you see, one of your friend may think that I will consider the jobs in the ascending of order of starting time. Whichever starts first, I will assign that. Then which it is the expectation that that will finish first as early, because if I start a job which is starting time is earlier, then I may be benefited. I may be, please remember, I may be benefited. So it is called earliest start time. This is the greedy idea. Another can be earliest finish time, means I will consider the jobs which finishes first, means in the ascending order of the finish time. This is another greedy idea. Or someone may think I will choose the jobs in the ascending order of the interval length. Means I will choose the job which takes minimum amount of time. Means minimum amount of time is finishing time minus starting time of that job. So I'll choose the smallest one, then the next smallest, like this. So in the ascending order of the interval length, shortest interval. Then fewest conflict. For each job, we will count the number of conflicting jobs, CJ. So schedule in an ascending order of conflicts, CJ. That means for each job I can count how many other jobs are conflicting with it. Means how many other jobs are overlapping with it. I will keep a counter. So I will sort them in the increasing order of the counter for each jobs, and I will assign in that way. So that is called fewest conflict. So you see there are so many greedy idea. It is not necessary that all the idea will give you the optimal solution. So that's why I'm saying you that it depends on practice and your intelligence. But please remember, you have to prove also. Means you can greedy designing an algorithm is very easy, but you have to prove also that it is correct. So check that greedy idea sometimes fails. For example, what was the first one? Earliest start time. Check. I will consider the jobs in the ascending order of start time. See, in this case, say there are 5 jobs. So according to this, tell me earliest start time, how many jobs will be allocated CPU to the CPU if I use the ascending order of start time for this? Anyone?
Sir, could you repeat the question, sir? My net kind of went off, sir.
But I am asking, the idea is that greedy idea is the earliest start time. The consider we will consider the job in the ascending order of the start time, SJ. So here five
Yes, sir.
jobs. 5 jobs are here. You check 1, 2, 3, 4, 5. So if I use that strategy, depending on the start time, then how many jobs will be executed?
One.
One, sir.
Only one. This black color means darker shape. Okay, but you see, if instead if I can allocate this one 1, 2, 3, 4, optimal answer is 4. But here it gives 1, so it fails. So this cannot give the optimal answer. So that means you have to take care of all the cases. Just no, don't only design, you have to take care. Next, break shortest interval. I told you that I will select the job that needs mm, small amount of time to execute. So according to this, you see in the next figure, it if I allocate means execute the smallest, then these and these cannot be executed. So here optimal answer is 2, this one and this one, but our solution gives 1. So this also failure. It okay, so it breaks. Then the break last one, previous conflict. For each job, we'll count the total number of conflicted job and schedule the smallest one. Then so with it, you see, with this conflict, it conflicts how many? 1, 2, 3. So its CJ value is 3 conflicting. For it, 1, 2, 3, 4. For it also 4. And for this, all of these conflicting values are 4. 1, 2, 3, 4. Here also C values are 4, and here C is 2. So according to this, our algorithm, it will choose which one? First this one, this black colored. Okay, so it will choose this one minimum. So if I choose this one, I cannot choose this one and this one. Fine. So from the remaining, I can choose one of them, say this one and this one here. So our solution gives, our solution means fewest conflict, gives 3 jobs, but optimal solution is, what is the optimal solution in this case? Tell me.
4.
4. So these also fails. So you can think that it may be okay, please. That's why I'm saying. But these are the special case. It has been shown where it fails. You may be benefited in some other example, but don't think that okay, you are getting benefit means optimal solution answer. That does not mean that your solution is really optimal. In a special case, it may fail. Now read this. There are 4 greedy algorithms for this problem. So the last one, another final one means if we sort the job in the increasing order of finishing time, increasing order of the finishing time. So this is matter. This gives the optimal solution. You will check it. Take each jobs provided it is compatible with the ones already taken. So these are the arguments S1, F1, S2, F2, dot 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 dot. This initially remaining means none of them has been selected. So 1 to n their ID. So selected is 0. So these are the all remaining and these have not been started. While remaining is greater than 0, what I will do, K will be, I will choose from the jobs that job whose finishing time is less. Means Fi, all the Fi, among all the Fi whose finishing time is less, that argument, minimum argument I. So that is K, that index. So selected will be selected union K. And remaining, from the remaining set, I will delete this. Now once I do this, means for every I in the remaining, see I have selected kth job. So for every I in the remaining, I have to check if Si is less than finishing time of Fk. See, this is the Sk and this is the Fk. Fine. Now if any jobs whose starting time I is less than finishing time of the kth job, then I have to reject that also, because I cannot execute both job K and job I. So if Si is less than the finishing time of K, then from the remaining portion, remaining square while loop is linear, the time complexity is not a matter, but we have to prove that it is optimal. So Or you can say like this, that what, how can I do that? Sort all the jobs, the same, for same problem, same algorithm. So consider the jobs in the increasing order of the finishing time. So sort all the jobs by finishing time, so that f1 f2 dot less than fn, means after uh, sorting I am giving the first one as the f1, then f2, f3, renaming. I am just renaming the jobs. Then take each jobs provided it is compatible with the ones already taken. I will consider the job if it is already compatible, means it is not conflicting with the ones that has been already chosen, already taken. So job selected is A. A is initially phi empty set. Now for j equal to 1 to n, if the job j is compatible with A means the jobs in A, then what I will do, I will include that j job into the A. Fine. In this way, I will do carry on and then return A. So sorting takes how much time? Sorting takes n log n time. We go up n log n time. Okay. So in the and here you please remember job j is compatible with A, that I have already said. If sj is greater than f. Now how can I prove that this is optimal? So basically exchange trick is used to prove. Exchange trick. The trick is exchange trick. Means I will exchange a job, means member of the optimal solution with my solution. So for example, we will prove that greedy algorithm is optimal. This is a theorem. So how can I prove? Prove by contradiction. So we assume that the greedy is not optimal. Our greedy solution is not optimal. And let us see what happens here. See, I have a solution I1, I2. So in this way, I have a solution. This is the I1. This is the I2, I3 dot 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 IR minus one, like this IR plus one, this dot, 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 up to IK. So this is the set of jobs selected by our greedy algorithm. Now optimal algorithm is there exists a set of jobs in the optimal solutions also. So let they are J1, J2 dot 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 JM, the set of jobs. So how many jobs here? The number of jobs is M. How many jobs in our solution? K. Now we have to show that K is equal to M. If K is equal to M, then in both the cases, the same number of jobs are executed. Maybe that okay, you are executing say job 5, 6, 8, 3 jobs. I am executing job 1, 2, 3, like that. But it can means the number of jobs are same. That we have to prove. So how can I prove this? So for example, we assume that I equal to j1, means the both these and these are same. I2 equal to j2 and IR equal to JR. In this way, up to these are they are equal, means same ID jobs in both optimal solution and greedy solution. Now greedy solution differs from the optimal solution at this index, means IR plus 1 and JR plus 1. Now I know our strategy chooses the job which finishes first. So from this remaining set of jobs after IR plus IR, the IR plus 1, the finishing time of IR plus 1 must be less than the job JR plus 1. Otherwise, I would have not selected IR plus 1. Clear? So job, I am sure that job IR plus 1 finishes before job JR plus 1. If it is so, then what can I do? I can, okay, this is job this, so why I can't replace this job JR plus 1 by IR plus 1? I can do this. So because here you see they are non-compatible, I mean not compatible, and I am just exchanging it, replace with this, and in this way I will go on for the last one also. Next one, next one, next one. So I will replace all the jobs of optimal solutions with our solution, and both in both the cases, the value will be same. Okay. So today I stop. If you have any question, you may ask.
Sir, one question, sir, could we get the like the slides that you taught today, sir? Because it would be very helpful, sir, because of the proof and all that.
I will upload. Okay.
Okay, sir. And sir, for the CA1, sir, could you list the topics that we have, like the broad topics we have, sir?
No, no,
Like the
I
six
have
topics.
already, told that just before the amortized time complexity, everything is there. Means,
Okay,
uh,
amortized is included.
no, no, not amortized
Only
is
till
not.
convex hull, right?
Convex hull, shortest path, closest pair problem, that majority finding, all other problems, those have been discussed already, na? Everything.
Okay. Sir, it would be very actually, sir, because of the videos, sir, because we don't have any